Hi, Christine.
Hi, Kanwal. Are you ready to do the show?
Just about. But this lighter is out of fluid. Can you give me a light?
Euclid. Give Kanwal a light.
Turn it off. Turn it off. Very funny, but that's not what I meant, Christine.
Are you sure? Hi, and welcome to the Math Shop, where mysterious mathematics is a way of life. Really. Kanwal and I and my trusty all-purpose computer Euclid are going to show you that mathematics is not just mental, it's visual as well.
That's right. There's one part of math that's all about making pictures.
And why pictures? Well, you can think of mathematics as a process of organizing and comparing information so you can make some sense out of it. And one way of comparing two quantities is to make a picture using a line graph. So, in this program, we'll show you how to graph a linear equation using something called the Slope-Intercept form. So stay with us. It's going to be fun.
Excuse me, Christine, what are you going to do with all this?
Well, these are props for the show, of course.
But...
No, well, never mind, Kanwal. Don't ask me now. I'll show you later. Why don't you show our audience about the candle first?
Oh, okay. A line graph is a way of describing a real-life situation very succinctly. For example, I know as this candle burns, it gets shorter. Suppose that I wanted to look at how the length varies over time. I could take measurements with my ruler and stopwatch and get Euclid to put it all in a table.
A table presents you with a lot of data. But to understand it, you have to mentally compare each number with every other number.
You might understand it much more clearly if you use the data to make a graph.
Like this. Euclid, graph mode, please.
One quantity on the graph could be the length of the candle, and the other could be the time it burns. The horizontal axis is usually referred to as the x-axis, and the vertical is the y-axis. In this particular example, we've chosen to represent time on the x-axis and length on the y-axis, but we could just as easily have done it the other way around.
We can learn something about the life of a candle from the line that is drawn on the graph. For example, which of these three do you think best represents a burning candle?
In this example, the length of the candle decreases gradually, then quickly, and then it slows down again, burning out very gradually. In situation B, the length of the candle decreases steadily.
I think that represents the situation quite well, Kanwal, but I have my doubts about C.
Yes, this really doesn't seem to fit the situation. This shows a candle that doesn't get any shorter at all while it burns, until all of a sudden it disappears.
But that last graph could be accurate if we just changed one label.
What do you mean?
Okay, like this. By changing the y-axis from length to light intensity, because a candle sends out a steady amount of light until it finally burns out, and then there's no light at all.
You're right. That's good thinking.
Gee, thanks. In fact, there are many everyday situations and events that can be graphed, and we've collected a few clips over the last couple of days. Euclid, roll clip 1. This is Anne. She told us that she earns $11.50 an hour. But if the store is busy and she works extra hours, she gets paid overtime. That's time and a half. So around Christmas or just before school starts, the amount of money earned can really add up by the end of the week. Or consider the case of Harold, whose gas tank holds 45 liters, and in highway driving, he can figure to use about 9 liters an hour. That means he could go for about 5 hours non-stop, if his family would let him. Another relationship that can be graphed is age and height. In this case, the graph levels off when we stop growing, sometime in our late teens. Of course, such a chart will be different for each child.
Yeah.
And if you've ever gone camping in the mountains, you may have noticed that your tea gets cold a lot faster when you're high up. That's because it doesn't get that hot in the first place. The higher you go, the lower the boiling point of water. That means it takes a lot longer to cook the potatoes, too.
So, graphs really can be helpful by clearly showing relationships.
Yeah, like my last relationship. Okay? Here's another practical example from my own life. Okay, I'm nuts about movies. I could watch these things all day if I could afford it. You probably know that just about every video store seems to have its own pricing scheme. Some have a membership fee, others don't, but they charge more per movie. So, if you're trying to stretch your entertainment budget, you'll want to know the best deal.
You might be able to decide by plotting a graph. Do you have the information, Christine?
Oh, yep, right here. Okay. I went to Megahit the other day, and Megahit charges $2.50 per movie, but there's no membership fee.
Okay. If we convert this to an equation for Megahit, C, the cost is equal to 250 times N, or the number of videos you rent in a month.
Down the street, their competition, Smash-O-Rama, don't charge a membership fee, but they charge $2.99 a movie.
So, in this case, the cost, C, equals $2.99 times N.
Right, and finally I checked Video Village, and they only charge $1 a movie, but there's a membership fee of $5 a month.
The equation looks a little different this time. C, the cost, equals $1 times N, the number of videos you rent in a month, plus $5 membership fee. Now, I'm going to get Euclid to graph these three equations, and you'll see how a graph can help you solve problems like these. Euclid, with Megahit, as you rent more movies, your cost increases steadily. Now, let's add Smash-O-Rama. Like Megahit, Smash-O-Rama increases steadily with the number of videos rented, but it increases faster. So far, it's an easy decision. Megahit is always cheaper. The line graph for Megahit is always below that of Smash-O-Rama. So no matter how many videos you rent per month, the cost at Megahit is always below that of Smash-O-Rama. But now let's graph Video Village and see how that looks. Yes, now it gets interesting. Even before you rent a single video from a Video Village, you're out $5 each month. But over the long run, it can be less expensive than either of the other two, depending on how many videos you rent.
This graph allows you to determine where the break-even point is.
The break-even points are here and here. At this point, Video Village is cheaper than Smash-O-Rama. And at this point, after you've rented your 6th video in a month, Video Village is even less expensive than Megahit.
In other words, if you rent more than 6 movies per month, then Video Village becomes the best buy.
Christine, are you sure you don't want to tell me what you're doing?
Not yet. Be patient, you'll see.
I hope so. Well, we'll come back and take a closer, more mathematical look at this graph. But now, let's talk about the concepts of graphing a line.
To begin with, a line on a graph has something called slope. Euclid? If you look at a line graph as if it were a road, you could say that the road, or graph, goes uphill or downhill, or stays flat. That's what we mean by slope. Reading from left to right, lines that go up have a positive slope. Lines that go down have a negative slope. And a line that is absolutely flat has a slope of 0. There is one other possibility, and that is a line that goes straight up. Of course, in real life, no road goes straight up. That's not possible. And it doesn't fit too well into mathematics either. A line that goes straight up and down is said to have an undefined slope.
In mathematics, the slope of a line is a value that can be calculated. It is defined as the distance traveled up or down for every unit traveled horizontally. The distance traveled up or down, in other words, along the y-axis, is called the rise, even when the slope is negative. The distance traveled along the x-axis is called the run. So the slope is equal to rise over run. I can show you what I mean with a few rubber bands and this thing called a geoboard. Now, in this case, I'll stretch the band over 3 points, making a triangle. And this sloping part of the triangle represents the line we want to investigate. We can calculate the slope by starting at either end point of the line. In this case, let's start with the lower left-hand corner. Now remember, just like on a number line, movement to the right is positive, movement to the left is negative. Likewise, upward movement is positive, downward movement is negative. With that in mind, let's calculate the slope of this line. The run is 2 units to the right. The rise is 1 unit up. The slope is found by putting the rise over run, or 1 over 2, which is 1/2.
As Kanwal mentioned, you can start at either end of the line to do this calculation. And as long as you pay proper attention to the signs of the numbers, you'll get the same slope.
That's right. If I start at the upper right corner of this triangle, I find that the change in the y-axis, or the rise, is actually -1, down 1. Change in the x-axis, or the run, is -2, moving 2 units to the left. Therefore, the slope is -1 over -2, which also equal 1/2. So, remember, you can calculate the slope of a line by starting at either of 2 points on that line. And it doesn't matter which 2 points you choose. Euclid, give us another example. Not that one. We just did that, a different one. This time we have a longer line which overlaps the previous one. The rise is 2 units up, and the run is 4 units to the right. So we have 2 over 4, which is equal to 1/2. The slope is still 1/2. In other words, the slope is a ratio of vertical change to horizontal change, or rise to run.
Okay. Kanwal, so far you've given us examples of a positive slope. Now what about a line with a negative slope?
Okay, here is a slope where you can go downhill. In this case, I'm looking for the slope of the line formed by the slanting part of this triangle. And remember, I can start at any point on this line segment. Let's start at the lower right-hand corner. And what is the run? 3 units to the left, or -3. And the rise is 4 units up, or +4. Therefore, the slope is 4 over -3, or -1.3 repeating. And, as we said before, when you're calculating, it doesn't matter where you start. If I had started with the upper point, the rise would be 4 units down, or -4. And the run would be 3 units to the right, or +3. Which makes our slope -4 over 3, or once again, -1.3 repeating. And slope of -1.3 repeating is the same as a rise of -1.3 repeating and run of +1.
You can see one practical application of slope when you're driving through the mountains. Sometimes you'll see a sign like this. And maybe think 8% doesn't sound like much, especially when you'd like to get 100% on a test. But that sign is telling you the steepness of a hill, calculated as the rise per every 100 meters. In this case, we have a rise of 8 meters for every 100. The equation would look like this. And a rise of 8 over 100 is expressed as 8%. To put that in perspective, I have some images to show you. Euclid? Roll clip 2. We can say that an 8% grade would usually be appropriate for a wheelchair ramp, although some ramps are as gentle as 5%. However, during his Man in Motion tour, wheelchair athlete Rick Hansen made it up Thermal Drive in Coquitlam, which at its steepest has a grade of 16 to 18%. Now that's a positive slope.
So, using what we know, now we can take any 2 points and calculate the slope of the line that connects them. Let's give Euclid the coordinates of 2, 1 and 5, 7.
Remember that you can specify any number on a graph by giving a value for the x-axis and a value for the y-axis. And just like in the alphabet, we write the x before the y.
Exactly. which means this first point is at the intersection of positive 2 on the x-axis and positive 1 on the y-axis. The other point, we do the same thing, find 5 on the x-axis, 7 on the y-axis. Then I join them with a line. And that is the line for which I want to find the slope. So, let's start at the lower point and calculate the rise. It starts at 1 and goes to 7. How far do we rise? 7 minus 1 is 6. We can calculate the run in a similar fashion. It starts at 2 and goes to 5. How far do we travel on the x-axis? 5 minus 2 is 3. The run is positive 3, so the slope is rise over run, or 6 over 3, which is equal to 2.
So now that you're pretty comfortable with the idea of slope, let's take a look at another important characteristic of a graphed line, the intercepts. No matter where you draw a line on a graph, if you extend the line far enough, sooner or later it's going to cross both the x-axis and the y-axis, unless of course the line is either horizontal or vertical. Where it crosses the x-axis is the x-intercept, and where it crosses the y-axis is the y-intercept. Take a look at another one. In this case, the y-intercept is equal to 3, and the x-intercept is equal to 4. Euclid, some random placements, please.
If you look at these lines, you will see that x-intercepts always have coordinates of some number and 0, and the y-intercepts always have coordinates of 0 and some number.
Now suppose you know the slope of a line, but you don't know anything else. In that case, you don't have enough information to graph that line. For example, Euclid, could we have a slope of 1, please? Intercepts unknown. This line has a slope of 1, no matter where we place it on the plane. In the same way, if we specify just the y-intercept, Euclid, a line with y-intercept of -2, please. We know where it crosses the y-axis, but we don't know the slope. However, if I have both the y-intercept and the slope, let's say a slope of 1 and a y-intercept of -2, then my information describes one line and one line only. No other line has these same values.
There's an equation which allows us to find the slope and the y-intercept quite easily. It's called the slope-intercept form, which is y equals mx plus b, where m is the slope of the line and b is the y-intercept. Now, to try to understand this equation, let's start with the simplest form. Just 1x and a value for b of 0. An even simpler way of writing the statement is y equals x. If we plot this, we notice that the line intersects the y-axis at 0. If we increase b to 1, our equation becomes y equals 1x plus 1. And we see that the point of intersection with the y-axis is now 1. In the same way, if we increase b to 2, our equation becomes y equals 1x plus 2. And now, the intersection is at 2. So, it is very clear that b is the y-intercept. Whatever value we substitute for b will be where the line crosses the y-axis. Now, let's look at our graph again and see what happens when I change m if m equals 2. I find that the slope is steeper now, more positive mathematically speaking. But suppose I change m to -2. The slope changes direction. It's no longer positive. Now it's negative. But notice that the y-intercept given by b did not change. And if I set m at 0, I get this equation, y equals 0x plus 2. And because anything times 0 will be 0, it's really the same as this, y equals 2. When I plot this, I get a flat line with a slope of 0, but still the same y-intercept. So now you can see that in this slope-intercept form of a linear equation, m is the slope and b is the y-intercept. Therefore, if you can rewrite an equation in this form, you can easily graph it. For example, in this equation, y equals negative 2/3 x minus 1, the y-intercept is negative 1. So I start by plotting the point 0, negative 1. Next, I look at the slope, which is negative 2 over 3. Starting at the y-intercept, I plot the rise, which is negative 2, and the run, which is positive 3. And that gives us our second point. When I connect our points, I have a graph of the linear equation. And every pair of coordinates along that line will satisfy the equation.
So Kanwal, how does the slope-intercept equation apply to my shopping for videos? You said we'd get back to that.
Yes, this is a good time to do that. The equation for Video Village was this. Euclid, first we drop the dollar notation to make the numbers simpler. Complete the conversion by changing the c to y and the n to x. Now we have y equals 1x plus 5. So we can see immediately that the slope is 1 and the y-intercept is 5. And as Euclid will show us, the coordinates of the y-intercept are 0, 5. That is our starting point. The slope of 1 tells us that the rise and the run have the same value. So to graph this line, we could, for example, go up 1 for the rise and to the right 1 for the run. We could have gone up 4 and across 4. It would have given us the same slope. 1 over 1 equals 1, 4 over 4 equals 1, etc. And once we have two pairs of coordinates, we can draw a line which makes a picture of our information.
Just to recap, there are 5 steps to graphing using the slope-intercept form. The first is, naturally, to get your equation into the right form.
If you are looking at something like this, it is quite correct to add missing 1s and 0s to get the equation into the form y equals mx plus b. Now determine the slope m and the y-intercept b.
Then, on the graph, start at the y-intercept. In this case, the y-intercept is 0, or coordinates 0, 0.
Using the slope, plot the next point. The slope of 2 is easier to use if it's expressed as a fraction, 2 over 1. This tells you the rise over run, a rise of 2 and a run of 1.
And then draw the line by connecting the 2 points.
That is how a graph is plotted. But let's try putting graphs to work. Do we have anything to work on right now?
Yes, we do. I got an email from my old piano teacher, Mrs. Kaczynski. She's looking for a hall to rent because her daughter's getting married.
Oh, congratulations.
Yes, congratulations, Mrs. Kaczynski. Finally got rid of her, huh? Anyway, one particular quote stated a cost of $5,000 for the hall, the music, the table and chairs and so on, and $20 per person for the food. They're still discussing the guest list, so they don't know how many people to invite, but she wants to know if we can help her with this part of the wedding. What do you think, Kanwal?
No problem. We can write an equation that will let her calculate the cost of any number of guests. But we can also draw a graph which will help her decide how many guests she can really afford without recalculating the equation each time. Let's start with the equation, then we'll move on to the graph. The cost C equals $5,000 plus $20 times the number of people, P, that attend. If we rewrite this in slope-intercept form, we get y equals 20x plus 5,000.
Euclid, give us a grid that we can use to plot y equals 20x plus 5,000. Of course, the scale is a little different from previous graphs to accommodate the numbers. The cost is on the y-axis, and we've indicated that a large portion of the y-axis is missing by inserting a break in that axis. And the x-axis shows the number of people. To see how this is plotted, we'll zoom in on the lower portion of the grid. Euclid, magnify, please.
To plot our graph, we start at the y-intercept of 5,000. Then, with a slope of 20, we move up 20 and over 1 to get our next point. Okay? Let's go back to full view. Euclid, full screen, please. Because we are working with large numbers and small divisions on the graph, it is a good idea to construct a table and plot at least one other point to be sure you're accurate. Once you have the points plotted, you can join them.
Mrs. Kaczynski needs a larger graph to predict the costs of bigger groups of people. So we need to extend the graph a little more. Euclid, extrapolate and print.
Mrs. K can now use this graph to estimate the cost of the reception based on the number of guests. For example, if she invites 100 people, it'll cost her approximately $7,000. If she invites 200, it'll cost her $9,000. If 300, then $11,000, and so on.
And I'll drop a copy of the graph off to Mrs. Kaczynski on my way home. Thanks for your problem, Mrs. Kaczynski, and good luck with the wedding.
I think that's it for today, except for one thing. I have to ask, what have you been doing with those coins and tubes and things?
Kanwal, I thought you'd never ask. This is a graph of my entertainment budget. You see, every month I start out with $60, and then I allow myself to spend $15 every week. And this line here shows me how much money I have left.
Well, after 4 weeks, you'll be out of money, just like this graph shows. But what's this extra column, and why does it have more coins in it?
Well, you see, because at the end of the month, I do this great big house cleaning, and I always find loons in the couch.
Financial planning according to Christine. I think we're out of time.
Right. Well, tune in next time to Math Shop, where we show you that mathematics can be graphic, but never violent. Oh, that's for me, probably. Math Shop, Christine speaking. Oh, hi, Mrs. Kaczynski. Oh, you saw the show? Oh, great. Sure. Powder blue? I love that. Oh, yes. Well, okay, well, just make sure that she doesn't throw the bouquet right at me. Okay, because, no. Yes, I am dating. Well, cute. Okay. Well, what about that little cake thing? Do I have to stick it under my pillow? Well, I just changed my sheets.